Welcome everybody to the Research Skills 101. We have a presentation today by Herbert Bernstein on doing science for research grant proposals. And we're going to have, Herbert's going to give us a presentation and then we'll have time for Q&A at the end of the presentation, if all goes well. So, and feel free also to add to the chat if you have any questions as we go along, and then we'll just have a collection of questions to answer at the end. So Herbert, I'm going to let you take it away.
Thank you. Well, good evening, everybody. We're going to talk about doing science. Now, this may sound quite presumptuous, but the reality is that if you want to do research grant proposals for doing science, you have to follow some rules or you're not likely to get funded. Now, there are always exceptions. There are people who get funded for things that, you know, you may think that's not science, that's not research, that's not this, that's not that. But there are certain norms that have been in place for a very long time. And we're going to talk about what those norms are for doing what's called hypothesis-driven science. Okay? And now we have to get my machine to cooperate. Yes, it wants to bleep. You can hear occasional bleeps, because it's decided that the right thing to do when I push advance a slide is bleep at me before it advances a slide. Okay. Now, the intention is to provide you, my assumption, you know how to do science. This is review material. And it's to help you keep in mind some things that would belong in a good hypothesis-driven research proposal. Now, you have to realize that the conventions for, quote, doing science are going to vary. It's going to vary with the discipline. It's going to vary with the funding agencies. It's going to vary with the institutions involved. It's going to vary with the people engaged in the project. It's going to vary with specifics of the project. It's going to vary with whether we're having World War III or not at the moment. It will vary. So we're going to restrict our attention right now to empirical research. That means experimental research, in which we try to prove a hypothesis which can be challenged by data from physical experiments. And it is not possible to tell you everything you need to know in half an hour or an hour or a day, or possibly even a lifetime. But we're going to get started, and I'm going to recommend some books to you. One book I'm going to recommend to you is by Ian Viella, Doing Science, Design, Analysis, and Communication of Scientific Research. And I'm going to recommend the second edition. I think it's a very good book. You may not like it. You may love it. It happens that it covers a lot of the points that I think you should cover. There is also a book I think everybody likes, Fisher's How to Dunk a Donut, The Science of Everyday Life. That will give you a feel for, doing scientific experiments that are, in fact, quite valid science. Then there is what amounts to a math book, An Introduction to Measurement Theory and Experiment Design by a guy named D.C. Baird from 1995. That may sound like that's an ancient book. That's actually quite recent book. They're much older books. This one is a very good guide on designing an experiment. And then, you're not going to like this, I think. In order to be able to do empirical science in a fundable way, you almost always have to include valid statistical methods. You need to know statistics. So I selected a statistics book, which is at least entertaining. Norman and Striner, Biostatistics, the Bare Essentials. Almost any statistics book will do. You do need to learn statistics. It is important. Now, you also need to pay attention to ethical and responsible professional behavior. You are not going to be funded for long if you do not follow the rules of behaving yourself. So there's some professional issues you need to consider. One of them is not a matter of right and wrong. It's simply a matter of reality. It's called Murphy's Law. Anything that can go wrong will. You develop very, very conservative behavior, looking out for things that can go wrong. And the other one is called KISS. I didn't make this up. This is an engineering rule. It is taught in every engineering school. It stands for keep it simple. So far, so good. Stupid. The second S is part of the rule. Okay? You really have to assume that you, the people reviewing your research, everyone need a certain degree of simplicity, or will simply go beyond our intellectual capacity to cope with what the issues are. So anything that can go wrong will, and keep it simple, stupid. These sort of basic rules. You have to follow them. Then there are some rules which are going to get you in very, very big trouble if you don't follow them. You have to assume responsibility for human subjects. And I gave you the federal regulation, 45 CFR 46. And if you're not in the United States, don't worry. Almost every country has some set of equivalent rules. You have to pay attention to take care of human subjects. The reason you have to pay attention to take care of human subjects is many, many people doing supposedly very, very good science have done some very, very bad things. And you have to make sure you're not going to do any bad things to human subjects in the course of your science. Similarly, you have to assume responsibility if you're working with animals. And for some reason, there is a preference for protecting vertebrate animals over invertebrates. So the main set of rules are over vertebrates. But quite frankly, don't base your science on smashing spiders or something either. Okay? Be kind to, all God's creatures. You have to have responsibility for safety. I don't know if you know it, but organic chemists used to have the shortest life expectancy of all the physical sciences, because what they would do is they would decide on what they were dealing with by tasting it, smelling it, etc. That lots of unsafe practices. This had to be put an end to. It is pretty much been put an end to. Organic chemists now live almost as long as orchestra conductors. But that's because everyone has to follow the rules for safety. And you are definitely responsible for scientific integrity. I picked out one of the school guidelines from Pitt, for example. They all have them. You have to follow them. I'm sure you'll all remember all the lectures you got as undergraduates in college about don't plagiarize. It's sort of the basic idea. Show integrity and ethics in how you do your science. Do not present somebody else's work as your own. Behave yourself. And there's responsibility for intellectual property. There are laws on patents and copyrights, etc. Follow them. Okay, now we get to what it means to be doing science. And I like Vermeulen's first edition, his summary of what the material is. It's asking, testing, and communicating results about a scientific question above and beyond the knowledge you need about specific fields of study. You're posing a new question of some kind, and you're trying to ask the question. You're going to propose an answer. That's called a hypothesis. You're going to test the hypothesis, and please communicate the results. We're going to go through what the scientific method is. We're going to talk briefly about scientific writing, bibliographies, proposals, talks, and papers, very briefly. We're going to talk about the difference between models and reality. We're going to talk about the answers to questions. It's called, hypotheses, proposed answers. About forming a theory about how a system behaves. We're going to talk about observations. And we'll finish with one slide on fitting data. It's actually a very difficult subject. Now, everyone knows what the scientific method is. It's whatever scientists do. It's the process scientists follow to do science. For some scientists, it's purely theoretical. You formulate a theory on how various systems interact and what would or would not happen if they actually existed and they interact. That's theoretical science is a very interesting and challenging and entertaining thing to do. However, for most scientists, the process begins with a recording of measurable information. If you eventually have enough pieces of measurable information, some questions may come to mind looking at that information to ask about the relationships among those values. Now, there are, of course, times when a single value is enough to suggest an interesting question. Most of the time, you need multiple values. How many is multiple? I have to tell you, if you take a statistics course, you're going to have ingrained in your soul that multiple means at least 30. Okay? But yeah, it may be 1, it may be 30, it may be some other number. It depends on the question, depends on what system you're dealing with. You need a question to be asked. And the questions that you develop may suggest more theoretical models for the systems involved. And usually what will happen is, because we're dealing with pieces of information, some of which are independent and you set them, and some which are dependent and they come back at you from the system. You have models that are stated in terms of independent variables that can be set to produce measurable changes in dependent variables. Using those models that we have and that we create, you now try and take your questions and answer them in terms of the models in forms of hypotheses. And sometimes you are very, very lucky. The proof of a hypothesis sometimes comes from pure observation, just of observational research. But a lot of the time, what you have to do is some very carefully designed experiments. Now, you do your experiments, you get your results, and you're going to need to communicate. A lot of you already know that you want to communicate with somebody who's got money and explain to them why they should give you money. In other cases, you're not at that stage. You just want to communicate for the pure joy of convincing other people you've done something, you've answered some question. Science is of almost no value unless you communicate it. These days, the most popular ways to communicate scientific results is in the form of talks and papers. An important test of the truth and the value of scientific results is whether they can be reproduced from first principles and independent experiments by others, not by just you, but you've done your experiment and you provide a cookbook, a recipe for other people to see what you have seen. Now, results that survive this challenge could still be lost if you don't try and make sure that what you have done is included in the body of knowledge that future generations learn from. The key is publication. Now, it used to be when I was young, one of the rules of the game was you were not a scientist unless you could communicate in at least 3 languages. Then that dropped to 2. At the moment, we seem to be down to 1, English. I'm not sure how long that will last. But at the moment, primary language for science is English. And in addition to communicating out, in addition to just writing, you must read. You need to connect the science you are doing, the questions you are answering, to the science that has been done before and is being done by others. You need to put your questions in the context of past and contemporaneous efforts. So one of the tools you need to create for yourself and hang on to is a good annotated bibliography. It's very difficult to do scientific writing unless you have access to the things that have been done. And you're very, very lucky. When I was young, It was a much more difficult process, which consisted of spending hours and hours of days and weeks and months and years wandering through library stacks, pulling one thing down after another and reading it. Now you have Google Scholar. Makes it much easier, but not as much fun. I think library stacks are wonderful. And don't make the very common mistake of only citing the most recent work. When I review other people's works, one of the things I absolutely hate is when all you see is references that only go back 2 years. Almost every discipline only makes sense if you go through enough of the history to explain the origins of things and how they have evolved. Don't just do the last 2 years. Okay? So now I have been arrogant and pedantic and told you all the things you shouldn't do. Let's talk about what you should do. You need to organize what you're doing in terms of information which is categorized in terms other people will understand. So for example, there's nominal data, ordinal data, and measurement data. Nominal data is data that just has a name. Okay? It's not something being measured. You can try and quantify it by counting the number of instances. Ordinal data is something which can be ranked. Okay? You can put in some sort of an order, but you can't tell how different or similar things are unless they're absolutely identical. So most of what you will do with science, you like to have something which acts like a ruler. It's measurement data. It's not just ordered, but the differences in values give you a quantifiable similarity or difference. As a mathematician, the term I would use is a metric. Okay? And let me tell you, since most science is not going to be believed unless you do statistics, measurement data is really, really helpful in doing statistics. But it can be misleading. Little changes you make to your data, for example, squaring or taking square roots, changes these metrics, the distance between them, and can totally change the results of the test you're going to perform. Now, for most of science, you have to get used to an idea which really comes from computer science called a variable. A variable is a container for some related set of observed or generated information. If the values never change, you can call it a constant. If the value of the information in a variable depends on the values of the information in other variables, okay, it's called a dependent variable because it depends on the other values. If the values of information, the variables on which it depends, can be set by the experiment at particular values, those are called independent variables. Now you use your data and your variables, and for most purposes, you need to have a model. Again, you're very, very lucky. A lot of very good models have been built. In a field where I work, structural biology, we're talking hundreds of millions of models are getting built at an incredible pace. Okay? So it's nice to have a theory that explains how the variables interact. You want a theoretical model that mimics the essentials of the behavior of the real systems in which you're making your observations. Each system and subsystem will use some of its independent variables as inputs and some of its dependent variables as outputs. If we're lucky, we end up with some well-defined causal relationships between the inputs and the outputs, or at least some nice correlations among the variables. The classic example using, in correlations is the study of smoking and cancer. The thing that was first very clearly understood in smoking and cancer was the correlation between cancer and smoking. Which caused which? That took time to determine. But the starting point may be correlations. You look at them, and then you try and find causality. Now, The most useful models are the ones that are predictive. Those models allow virtual experiments to be performed just using the model, in which the results have not yet been observed and can be predicted. If the predicted results are then confirmed by actual observations, this tends to increase our faith in the validity of the models used. Models and reality are not the same thing. Now, all measurement techniques depend on models. There's some models assumed in the measurements, but actual observation is much more comforting. It makes us feel we're less likely to miss something. But a model has an advantage over actual measurements. The models have, simple relationships built in tends to suppress a lot of noise. It's cleaner and tends to be much more reproducible. Theoretical predictions and experiment results hopefully are going to agree. In the sense, what you would like is, as I get more and more experimental results, they provide better and better agreement to the theoretical predictions from the models, and more we get, the better the agreement, the happier you are. This is called the law of large numbers. But there's a problem you need to face. We take things and throw them together. Nature may not have. And you may have some sort of a system in nature which, instead of things all lumping together in one mode, what's called one normal distribution, they may actually be responding to some separate things. It may be multimodal. And we can lose that if we just average enough stuff. We can basically swamp things with our statistics. Need to be careful, okay? Now, the reason we're doing all of this stuff, collecting all of this data, is we're trying to find some scientific question for which we have an answer. A hypothesis is the statement of the answer to a research question. To be useful in deciding if we have an answer to the questions, the hypothesis needs to be testable. Unless hypotheses can be proven purely deductively from observations, there should be some experiment we can perform to show if the hypothesis is true or false. Most hypotheses related to measurable experimental data are difficult to prove absolutely true or false. For most practical physical experiments, the best we can do is estimate a probability that the hypothesis is true. And most of the time, we do not try and prove the hypothesis we really hope is true. We look at the antithesis of that hypothesis, called the null hypothesis. And we try and estimate the probability that the null hypothesis is false. And for the medical and social sciences, typically you try and get to a 95% chance that the null hypothesis has been disproven. That is usually considered sufficient data to be able to say that the alternative hypothesis, the one we really wanted in the first place, is true. Okay? Now, in order to put together these experiments, we tend to use things called treatments. We organize our information, okay, into experimental units. And then, those units have independent and dependent variables and constants. And we may create new derived variables, major change things. And we try and select appropriate statistical tests. This is risky. The drastic changes involved in creating treatments can lead to biased results, can lead to false conclusions. To improve the chance of an unbiased result, it's a good practice to take some of the groups of experimental units, and they are experiment groups, and others are what are called control groups. And the information in the independent variables in experiment groups are set to values intended to probe the hypothesis involved. The information in the independent variables in the control groups are set to values intended to provide data untainted by the experiments for comparison. And the best way to do it is we call it double-blind study. Information as to which groups are experiment groups, which groups are control groups, is concealed from the experimenter. Because the reality is people have their, what they want to have come out from an experiment. And if you have the person conducting the experiment knowing exactly what it is that's going on in the experiment, they may bias the result. Not intentionally, but it can happen and has happened. Okay. Now, you can have a very effective science done purely theoretically. The beating heart of a good research proposal is one, however, in which you have real systems that have real inputs producing real outputs. If what is observed differs in significant ways from what our models predict, this may be just random noise which averages out, but it could be systematic error. And then we may need to go back and change our measurement techniques, our theoretical models, or both. Now we need some tools to do this. All those math courses you didn't want to take as a high school student and undergraduate, go back and review them. You need linear algebra, you need calculus, and you need the tools from probability and statistics. And you got to be careful. They are very effective tools, but they're easy to use incorrectly. In probability, you need to get rid of the idea that you know what each result is going to be. Things are going to happen randomly, like tossing a coin. Okay? If the coin is something which is simply a disc equally weighted on both sides, when you toss it, you expect there's an equal chance the coin will land heads up or tails up. I hope you like my heads and my tails here. Okay. Suppose you toss a coin n times. Each toss should be an independent event. Later tosses don't depend on way earlier tosses work. In the long run, we expect half the tosses will have an outcome of heads and half the tosses will have an outcome of tails. So sufficiently large number n of trial tosses, we expect the ratio of h over n to be something that's close to a half, and get closer to a half as the number of tosses increases. We hope. Okay. That doesn't mean that any given run of tosses will come up half heads and half tails. It's possible to toss a fair coin 10 times and get 10 heads in a row or 10 tails in a row. In the long run, we expect it to average out. So the definition of probability is simply the limit of the ratio of the number of favorable outcomes to the number of trials. And there's all kinds of very nice things that happen if you assume things are independent, that they have disjoint outcomes. If we're looking at A or B and they are disjoint, the probability of A or B is just the probability of A plus probability of B. And the probability of not A is 1 minus the probability of A. Okay? As long as things are independent. And there's lots more rules here. Revive all your math, but before I put you all to sleep, we will just jump straight to the question of dice. Okay? I'm sure everyone loves playing dice. Okay? Every board game you get, you roll some dice. And it's just a matter of counting. If you're trying to get a 7, you get a 7 with a 1 and a 6, a 2 and a 5, a 3 and a 4, a 4 and a 3, a 5 and a 2, or a 6 and a 1. Okay? So there's one chance in 6 by taking those 6 out of 36 possibilities about how you can roll 2 die. One chance in 6 of getting this 7. Okay? That's all probabilities are, ratios of favorable outcomes to total number of trials. And this allows us to compute things called an expected value. An expected value is simply the weighted sum of the probabilities which go into it, where the weight is the value of what we get. And this can allow you to be a very, very good gambler and learn that if you go with the old form of a lottery, which only had 48 numbers instead of 50 some odd numbers, then your expected value of putting $1 million in lottery tickets is a little more than 8 cents. I trust that may cure you of lottery tickets. Okay. Now, we have probabilities. We then can have random variables. Okay. That if we have random variables, they could be like the spots on a die, discrete and finite. They could be discrete but not finite. It could be an infinite number of possibilities. They could be things which are like the real numbers, like heights of people. They could be continuous. And there are lots and lots of probability distributions. And there are a couple of very, very important things about probability distributions, which then become what are called descriptive statistics. Two very, very important ones are the mean and the variance. The mean is the expected value of the thing that is varying. It's the weighted sum of the values of x. That's usually called mu. The u with the funny stroke on it is a mu. Okay. And the variance is usually called sigma squared. And if you know mu and you take the expected value of the variable minus the mean squared, that's called sigma squared. Okay. And the square root of the variance is called the standard deviation. And this gives us a very, very important statistic that we can use called the z-score. And the z-score of x is x minus the mean divided by the standard deviation. Okay. For a continuous random variable, you don't get to say what the probability is of any individual value. The probability of any individual value is in general 0. Okay. So what you do is you add up the area under the probability distribution curve, okay, over a range of numbers. And that gives you something, in a particular interval, to something meaningful. The probability distribution is never negative, and the total area under the distribution curve always adds up to 1. And fortunately for your sanity, there are only 2 that you really need to know in your gut. One is the Gaussian distribution or the normal distribution, and the other is the Poisson distribution or the exponential distribution. Okay. When we take many samples from any distribution, okay, that gives us something where, we're sampling again and again and again, same distribution, and we go further and further and further. This will approach a Gaussian distribution. Okay. Formally, the theorem is called the central limit theorem. It says the average of n samples from a distribution with arbitrary density function is the expected value mu, and the standard deviation sigma. Okay, approximating a normal distribution with that expected value, and the standard deviation sigma over n, where n is the number of trials. In other words, you get a sharper and sharper normal distribution. The Poisson distribution is the one you see in arrival times of independent events, like radioactive decay or wear and tear failures. It's the basis for saying trouble comes in threes, in the sense that multiple events from Poisson distributions tend to come in clumps. And the probability density function of the Gaussian distribution I've given you on this slide, it gives you a thing that's called a bell-shaped curve. And the Poisson distribution is the thing that is just falling and dying out. That is the radioactive decay. And the 2 formulas, no, you do not have to memorize them. You will find them in any statistics book. Remember the bell-shaped curve and the radioactive decay. Okay. Now, There's another form of probability other than the expected number of favorable outcomes divided by the number of trials. It's called the Bayesian analysis. A Bayesian analysis is something which is becoming increasingly important. It is the understanding of estimating probabilities in the presence of prior knowledge. I've got prior information, for short, we just call those priors. Okay? And if we have prior information and we make use of it in estimating our probabilities, what we end up having to do is we basically assume the things that we are assuming are the entire universe of possible events, and we scale things up by dividing by that probability of the things we knew before. And it allows, very nice estimations in our estimate of new probabilities. The standard approach is called a frequentist approach. Bayesian analysis is not always the right way to do things, but it's becoming more and more important because we are collecting more and more scientific data that we can make use of in our experiments. In my field, there are now over 200 million models for structural biology, which can be used as priors in doing a new structure. It is very, very effective. Now, you need to include statistics in dealing with hypotheses. As a minimum, you almost certainly will need to, if you've collected any data at all, need to have some descriptive statistics on the stuff you collected. But the heart of the matter comes in making inferences from the statistics, estimating that this drug will or will not be safe to use and will or will not cure that disease. Okay, that's inferential statistics. There, you have a lot you need to do in order to get to a sound inference, and the best you're going to do is a probability that your inference is correct, but it is worth doing. And it is almost always done in some sense on the basis of that z-score. And as I said, for a lot of scientific testing, the criterion is the 5% limit. Okay, that's one-sided 1.64 standard deviations, two-sided close to 2 standard deviations. In the hard sciences, you very often try for better statistics than that. 1%, 0.1%. The most people have gotten to is something which is called 6 sigma, 6 standard deviations, and that's 0.0000001%. This may sound ridiculous, but in case you haven't noticed, almost all automobiles until recently were being made out of the United States. And the reason was the difference between 0.01% statistics and 0.00001% statistics, 3 sigma versus 6 sigma, because it turns out if you're looking at wear and tear of bearings and axles, the difference in wear and tear of a fit between bearings and axles of going between 3 sigma and 6 sigma is an entire market in automobiles. Okay. Now, I've told you before about the null hypothesis and the Olden hypothesis. If you have enough data to estimate probabilities, you can estimate alpha. The probability to sample from the null hypothesis supports the alternative hypothesis, and beta, the probability of a sample from the alternate hypothesis that supports the null hypothesis. This is all very, very useful. One of the things we are very often missing in trying to do any of this is knowing what's in the actual population. Part of it has to do with, double-blind studies. Part of it simply has to do with physics. Getting at actual population things can be hard. So we end up having to estimate those as well. And it means that we only get to estimate the probability of the truth of our answer to a scientific question, not to just know the truth. Okay? Now, a lot of this will depend on figuring out what we've got several different clusters, whether one cluster is the same as another, whether one Gaussian distribution is a distinct distribution, or we're just looking at different pieces of the same elephant. The techniques that are used and are generally called analysis of variance. The simplest one is when we're dealing with two clusters in one dimension, you use a thing called the student t-test. When you're examining more than two clusters in one dimension, we use one-way ANOVA. That's analysis of variance. And for examining clusters in more than one dimension, we use multivariate ANOVA. Please don't run away thinking you now know all the statistical tests you need to know, but you can get a pretty long way on just the student t-test. Okay. Now, last slide before you get to ask me questions. See, I didn't use the whole hour. I'm being good. Behave myself. I can talk approximately forever. All right. One of the things you need to do is convince people how well the relationship between your data and your model fit each other. And so you need to do fitting of data. Okay. Now, sometimes you are in a wonderful case of having what's called an overdetermined system. And that is that you have many, many more data points than you have degrees of freedom in your model to adjust things to get a fit. In those cases, in an overdetermined system, you can do what's called least squares methods. And you adjust the parameters of the model equation to minimize the average differences between the model values and the actual observations. For the longest time, most people wouldn't touch anything other than an overdetermined system. We're in a new world, especially in structural biology. A lot of other places, people are learning to live with underdetermined systems. Now, the guy who first did a really good study on how to live with an underdetermined system was a guy named E.T. Jaynes in the 1950s. And the technique that he developed is called the maximum entropy method. It comes from statistical mechanics. And what it does is look for the smoothest, least biased fit consistent with the data and strongly related to Bayesian statistics. Yes, you can misuse it. But I will tell you right now, this is so good, even though it uses a lot of computer time. It's used by the CIA and the NSA to read license plate numbers in satellite images. So that really must be good. And I think that is a wonderful note on which to say, any questions?
Great. Thank you, Herbert. That was a wonderful, I learned so much. What a great refresher.